Michael Klein from the Nautilus Group, here to go over the Chapter 1 assignment, questions 4 and 5 for CST 311. Some background information. We're asked to consider the network scenario in the figure to our right. Here we have K number of sources that are connected to the internet via links of capacity. We have sources designated by S and their links of capacity RS, and we've got destinations designated by D and their links of capacity RD. And these are connected via the internet with a common link of R. With this information, let's take a look at our first question. 4 says, suppose that K equals 10, that's the number of destinations, RS equals 100 megabits per second, that's the capacity for our source, RD equals 54 megabits per second, that's the capacity for our destination, and R is 50 gigabits per second, and that's the shared common link capacity. We're asked, what is the throughput between each source-destination pair? And we're given multiple choices. Step 1, we need to put all units to the same unit. This is very important, not just in computer science, but in all the sciences. In our problem, since we have 2 units that are megabits per second and 1 unit that is gigabits per second, it makes the most sense for us to convert gigabits per second to megabits per second. We're going to do this using some algebraic dimensional analysis. If you're not familiar with dimensional analysis, there's some great videos out there, and I would encourage you to become familiar and very practiced in it, as this will be useful to you in future computer science classes and also other science classes. I also would encourage to pay attention to the units. Here we can see the difference with megabits per second and gigabits per second, but sometimes the difference is more subtle. If the B was capitalized, we would be looking at bytes, not bits, and that is very different. So it's important to pay attention to units and to make sure that all units are the same. For our problem, we're going to convert 50 gigabits per second to megabits per second. We do so by setting up 50 gigabits per second over 1. We're going to multiply that by our conversion factor, which is a ratio of 1 gigabit per second to 1,000 megabits per second. Now it's important that the gigabits per second are top and bottom from each other when we're multiplying our conversion factor. And this is a good way to kind of keep straight what should be on top and what should be on bottom. Whatever you're canceling needs to be top and bottom from each other. That will allow us to cancel gigabits per second with gigabits per second. This will leave megabits per second, which is the unit that we want to convert to. And so in doing the math, 50 times 1,000 gives us 50,000 megabits per second. We now need to find the relative capacity for the common link R based on the number of destinations K. We'll recall that K was 10 and that R was 50 gigabits per second, or 50,000 megabits per second. Now with our formula, we have to take that common link of capacity R and divide it by the number of destinations K. Doing so, we divide 50,000 over 10, which gives us 5,000 megabits per second. We're going to compare the various capacities in our network. We have RS, our source capacity, which is 100 megabits per second, RD, our destination capacity, which is 54 megabits per second, and our common link capacity divided by the number of K destinations, which gave us 5,000 megabits per second. When we compare those three values, we see that the common link divided by K is the largest, Then comes our source capacity link, and then finally our destination capacity link, RD. And so we can see that the limiting capacity, or the lowest capacity, is RD in this case. What does this all mean? Well, throughput is based on the lowest capacity in a network. Therefore, since our lowest capacity in each source destination pair is RD, or that destination capacity link, we know that the throughput between each source destination pair will be 54 megabits per second. If you think about it, networks flow just like water flows in pipes, or traffic flows on streets. And throughput, the amount of flow, the amount of things getting through any sort of network, whether it's streets, water pipes, or our actual internet, is going to be limited based on the smallest point that allows things to get through. So our limiting or our lowest capacity will always dictate our throughput. We know, looking back at question 4, that the throughput for each source destination pair is going to be RD, which is 54 megabits per second. So we can select that answer. Question 5 is a follow-up question connected to question 4, and it asks, what are the bottleneck links in question 4? And we're given some choices. R, our common link, RS, the link of our source, and RD, the link capacity link for destination. Really a conceptual question. Bottleneck links correlate to the throughput, where the bottleneck link is the link with the lowest capacity. We already know that throughput is the amount of capacity for that limiting capacity. In other words, the throughput will be the amount of capacity of the bottleneck link each and every time. And again, looking back to the analogy of traffic or water going through pipes, it makes sense that the place where the least amount of throughput or the least amount of capacity is also going to be the place where things bottleneck up. And so therefore, we already determined that the destination link of capacity, RD, is the link with the lowest capacity, so therefore it is our bottleneck link. 5 again, we know that the bottleneck links in 4 will be RD, and we can select that answer. My explanation for questions 4 and 5 on the Chapter 1 assignment. I hope it's been helpful. If there's any additional questions, comments, feedback, I welcome it on the forum.